Welcome to qnawire.
So here we have a steam power plant operating on an ideal regenerative Rankine cycle. We have two open feed water heaters, so here, here, and here. And we need then three pumps. So again, I've drawn a little schematic here because it's starting to get confusing with all the stuff going on here. We have a mass flow rate through the turbine of 16 kilograms per second. What else do we know here? High pressure side through the boiler is 8 megapascals. Low pressure side through the condenser is 10 kilopascals. Steam is extracted at 600 kilopascals and at 200 kilopascals. So here and here. So then we have mixing in here and then mixing in here. Through the condenser, then we have these are all saturated liquid, we assume, coming into these pumps. And so we pump up from here from 1 to 2. And then at 9, stuff coming in from 9, stuff coming in from 2, exits at 3. And then likewise, we have mixing here at this junction. And then everything goes into the boiler and we heat it up again and we continue the cycle. So we have a lot of stuff going on here. So let's try to kind of get this what we can get out of here. So we know the temperature up at the entering the steam in the turbine is 550 degrees C. What else do we know? I think that's Wiley's saturated liquid. Yeah. So we can get the work from each of these pumps. So pump 1, pump 2, and pump 3. So because we can find the enthalpy coming in, and we can find the specific volume coming in, and then we can get the work from the specific volume and the pressure change. And again, we see here that most of the work is done by this last pump here, getting everything up to the boiler pressure. Obviously, this is really not all that much to scale because, you have 8,000 here and 600 here. So these things would actually all be kind of compressed down to the bottom, but then we'd be hard to see. So this isn't really to scale. Now, then we can then get the enthalpy at 2, at 4, and at 6 because we know the specific work before that in the pump, and then we just add this to this, this to this, and this to this, and we get all these enthalpies coming out of our pump. Now at 7, we have pressure and temperature. So we can get enthalpy and entropy. Again, I need to should make a note here. S7 equals S8 equals S9 equals S10, and then S1 equals S2, S3 equals S4, and S5 equals S6. So everything is ideal. The pumps and the turbine are 100% efficient, or yeah, or have 100% thermal efficiency, or isentropic. So then we can get, let's see here, we can get enthalpy and entropy at 7, and so then at 8, we know the enthalpy is the same as this, so then we also know the pressure, so we can get the enthalpy there. So we have the entropy and the pressure will give us the enthalpy. Now we have, we can figure out at 9, again, now the entropy at 9 is the same value here, but now the pressure is lower, 200 kilopascals, and we see that it's now in saturated. Now it's in the two-phase region here with a quality factor of about 96%. And so then we can get the enthalpy at 9. And then again at entropy at 10, and we know the pressure, so we get the quality factor is about 83%. And then the enthalpy there we can get. So let's see, we have the enthalpy at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have the enthalpies everywhere. So now we can start looking at conservation of energy and conservation of mass. So the feedwater heater 2, we have the enthalpy flow in from 8 and from at 4 and coming out at 5. So that's this guy here. And so we know M5 is the same as M.7. So again, M.5 we can think of as the mass is the flow rate to the boiler, and then in through the turbine or into the turbine. So taking that as our basis, we divide through and then define y as M3 over M5, and so we get M8 over M5. M.8 over M.5. So then we get the y equals 0.072 roughly. So about 7.2% of the steam is extracted to go into feedwater heater 2. So here we extract some to go into there a little bit, but 7% bleed off. And then looking at the first feedwater heater, again, we know, and again, I've used mass conservation because we have mass M.5 has to be equal to M.8 plus M.4. Same like with 3, it needs to be M.2 plus M.9. Okay, so I've used mass conservation in these two. So now in this case, we have enthalpy flow in to the feedwater heater, then out. And if we define Z as M.9 over M.5 and divide through and use conservation of mass, we get that our expression here, and this is an expression that we know Y and we know these enthalpies, so we can solve for Z, and that winds up being about 12%. So Z is the amount coming off of here. So we take about 12% down at 200 kilopascals. You take about 12% of the steam off there, and then use it to heat up some of this fluid, this water coming out of the end of the turbine. So let's see here. Then we have heat transfer in. Again, we just from here to here get that. Looking at the boiler, looking at the condenser, we can see that in the condenser we have to subtract off Y and Z because we've filtered off that. And so if this is 1 and this is Y and this is Z, then the mass here, the ratio of the masses here is 1 minus Y minus Z. So, and then the change in enthalpy there. So we get the heat transfer out in the condenser. So then we can get the net work is this minus this. And then the net power, we know the mass flow rate at 7, which is the same as at 4 and at 7 and at 6 and at 5 are the same. So we can multiply, that's 16 kilograms per second. So 16 kilograms per second times this specific work, and we get about 19.8 megawatts. And finally, we can get the thermodynamic efficiency is, well, this is one way of doing it. Other way we could take this divided by this, either way. And we get that is about 43.5%. So pretty efficient compared to some of the other systems that we've looked at. So like in the previous, this was 37.8. This was also 37.8. So now we've got it up to 43.5.